Okay, today we're going to continue with where we left off with motors, but we're going to do the reverse. So let's just quickly review. When we had a loop of wire between a magnet, so if we had our current going through the loop of wire, we had our north and south magnets around this. Remember that we could use our left-hand rule to figure out that the force would be upwards on this wire, into the page on that wire, so we'd get this motor to spin around. And then with motors, we just have to alternate the current, remember, so that every 180 degrees the current flows the other direction, and then that keeps our force spinning around and around in a circle. So that was how a motor works. So now what we're going to do is figure out what's the reverse. If we pass current through a wire in a magnetic field, that creates force. So scientists thought, well, will the reverse work? If we force a wire with no current through a magnetic field, would we then create current? And there were several scientists that did this. They were working on this roughly around the same time, and Michael Faraday ended up being the first to publish it. So there was an American, Joseph Henry was his name. They both kind of figured out at the same time, but Faraday published it first, so he's the one that gets credit for it. So Faraday called it electromagnetic induction, and the logic was, well, if we can create a magnetic field through a wire, then we should be able to create current. So the experiment he used is pretty basic, and what he thought of was, well, let's hook a battery up to a coil of wire around a metal, and he used a ring just so that it would pass it easy. So if you look at this, if we use our left-hand rule, and let's suppose our current goes in this direction, we'd use our left-hand rule and we'd see that we'd get a north and south pole of that coil of wire. So that's going to turn that coil into a magnet, so the iron ring would have a magnet on the other side. So then his logic was, well, if this becomes magnetic on this side here, and it really doesn't matter which way it goes. So if the coil, the magnetic field turns the other coil into a magnet, then the logic is then that should pass a current into the ammeter to be detected. So what Faraday did is he set up his experiment like this. He closed the switch and thinking it's going to work and he's going to get current, but he noticed basically nothing happened. When he closed the switch, the ammeter still showed 0. So then he thought maybe it was a mistake, so he unhooked the battery, rehooked it up again, and just by fluke he noticed that when he closed the switch on or off, the ammeter blipped, but then it would go back to 0. So just like you would do, he basically flicked the switch on and off very fast, and what happened then is he saw that he could actually create a current. So the current would stay fairly consistent if he went really fast back and forth. So his theory, his Faraday's electromagnetic induction law, is basically if we have a changing magnetic field, so as long as the magnetic field's changing, then we're going to be able to create a current. So using that logic, all he had to do really is, instead of switching the switch back and forth, all he had to do was basically move the ring. If you spin the ring, that's going to change the magnetic field, then you should be able to get a current. And that's pretty much how a generator works. So a motor, we use electricity to make it spin. A generator, we get something to spin, and that's going to create the electricity. So if this iron ring is spinning around and around, then we get a constant supply of electricity. So what we're going to do is, instead of looking at something complicated like that, we're going to keep it pretty simple. We're going to look at just pushing a straight wire. So instead of having a ring, we'll have a wire. So let's suppose we have a wire in this direction, and let's suppose we're going to push it to the right, and we're going to push it through a magnetic field that's coming out of the page. Okay, so the idea then is if we push this wire in the magnetic field, we should be able to generate a current. So the challenge is, if you're going to push this thing, which way is the current going to flow? So we use our left-hand rule again, but we got to be really careful. Can't use it the same way we did before. So our B finger is out of the page. That's still the same. So our B goes out of the page. What we got to be careful of is we're pushing this thing to the right. So that's not our F. So we don't put our F finger to the right and then our thumb. If we do that, we'd have B going up, F going to the right. So then our thumb would be pointing down. So we think that our current is going down, which is wrong. So what we have to do is we have to make sure we're really careful with our fingers. So in this case, let me just kind of re-sketch it. So we're going to push it to the right again. Our B is still out of the page. So we want to keep our B finger out of the page. But instead of it being a wire, think of it like being just one electron. So we're actually forcing that electron to the right. So we put our B finger out of the page, our thumb to the right. Now we get our force going upwards, and it's that force that's going to push that electron upwards. It's going to move the electron upwards, which then is going to create a current if there's a whole bunch of electrons. So it works the same. You just got to remember that your F finger now is the direction of the way the current's going to go, and your thumb is the whole wire being pushed one way or the other. And that's really the only trick. As long as you get that straight, the rest of it works exactly the same. So for this example, number 1 at the bottom of the page, let's try it. So put your thumb downwards. We're pushing the wire downwards. Our B is into the page, so put your P down into the page. So our F would go to the left. So that means that our current then is going to flow to the left. And that's all.